Hello，你有听到声音吗？是麦克风的声音吗？还是我声音？没有，对不对？很小声，对不对？喂喂喂，喂喂喂喂喂，我们今天就只能用这支。好，Slide 14。Slide 14. Heterogeneous reactions. Heterogeneous reaction involve two phases. If the reactant is gas, we usually use partial pressure to replace concentration. So at slide 14, the first equation喂，我要放弃了，录影没有声音哦，可是它有收音哎，那我拿着它，但麦克风没有用，好，就是这样子。Slide 14. Use ideal gas law to convert concentration to pressure or convert pressure to concentration. So ideal gas law is important for gas. Okay. And the second point, rate of reaction per unit weight catalyst minus RA prime. And the reaction rate per volume minus RA. What is the relation? What is the relation between these two? If you want to find the relation, you can write down the unit, right? Write down the unit. Oh, let me change a little bit. Okay. What's the relation between these two? The unit for minus RA, moles, time, and the volume, right? Moles, time, and the volume. What is the unit for this one? Still moles, time. But it is not volume. It is mass, right? Mass of catalyst. So to convert these two, you have to multiply something with the unit of mass over volume. Right? For the unit, equivalent of unit. To have equivalent unit at both sides of equation. So, do you know what is the physical parameter for this with this unit? It is called density, right? So to convert these two based on volume and based on mass, you have to multiply density. And this kind of density, we call it as bulk density. Bulk density. And the symbol, rho B. I think I will explain bulk density later, but I can tell you now we can have twice chances to understand what is bulk density. So there is a PBR. So inside of PBR, solid catalyst. Right. So I want to talk about two different density. One is the normal density. The other one is bulk density. So you can tell the difference. So the normal density, mass, volume. This one is also mass, volume. Okay, but of something different. This part is different. For the normal density, if you want to talk about the density of catalyst, the mass of catalyst, right? The mass of catalyst over volume of catalyst. It is the normal density. What is the bulk density? Mass of catalyst over volume of tube. Volume of tube. So it is different. So if we talk about the bulk density of the catalyst for this one, you can measure the mass of catalyst, right? You put the catalyst inside the tube, so you can measure the mass first. And after putting the catalyst in the tube, you use the lens, the radius, right? So the area multiply the length. This is the volume of tube. A little bit different, right? But this one is easier to calculate because if you want to measure the volume of a catalyst, it is harder. It is harder. But you want to calculate the volume of tube is easy because you know the size of the reactor. So this is called a bulk density. This is called like a normal density. So do you know which one is larger? The volume of tube is larger than the volume of catalyst, right? Because there are some space, there are some poles between the catalyst. So this one is smaller. The volume of catalyst is smaller, but the volume of tube is larger. Therefore, okay, their relation. The normal density is larger, always larger than the bulk density because the volume of tube is always larger than the volume of catalyst inside the tube. So that is the relation. So if you want to be more specific, you can just have some note. This is the volume of tube. Okay, this is the volume of tube. This is the mass of catalyst. Okay. So the difference between them called the bulk density, not the normal density. Any question? 一下麦克风。Okay, so let's go to the next section. Slide 15, reversible reaction. Actually, it is the rate law for reversible reaction. Okay. We're talking about rate law in part 1, right? So how to write a rate law for reversible reaction? Slide 15. Consider reaction. There is a reaction. I have written down this before, I think. Reversible, right? Reversible reaction. So you have the rate constant, Kb, K minus B, at both sides for the reversible reaction. And we can use a symbol. So next, I will write down the rate law. The rate law in forward direction and the reverse direction. Okay, 2 directions. So first, for the forward reaction. The forward reaction, it is one way, right? So to be become these 2 forward reaction. So what is the rate law? What is the rate law for this one? Assume they are all elementary. They are all elementary reactions. Minus RB for the forward reaction. Okay, forward reaction. You can write the rate constant here, Kb. Rate constant Kb. So forward reaction, the rate of B, reaction rate of B is like this, right? Because it is elementary. Elementary reaction means the order is the same as the coefficient. The order is 2 because the coefficient of B is 2 as well. You can also write a rate law, use the positive side, right? And the minus means disappearance. Okay. So next, talk about reverse reaction. Reverse. Okay, this is a reverse reaction. Again, the rate law, okay. RB reverse. Can you see?我写着 RB reverse。So we always write down the rate law using concentration of reactant. So for the forward reaction, the reactant is B. For the reverse reaction, the reactants are D and H2. Okay, so in the rate law, we use CB for forward reaction, CD and CH2 for reverse reaction. Okay? Following, go to next slide. You can write down then at the next slide. So let's combine the forward and the reverse rate law. So we got a formation. This is the rate of formation of B. Formation means positive side, okay? Formation. So this one is formation of B. Formation of B. So in forward reaction, B is constant, so forward of B is negative. Okay, so the rate of formation of B, we call it RB. Okay, RB is defined as RB forward plus RB reverse. So two ways. You write down the rate law in two directions and sum up together to find the rate of formation of B. So it is equal to So in the future, if you want to write down the rate law for reversible reaction, you can directly write down this one, okay? If you can directly write down this one, you don't have to analyze like that. This is the first point at slide 16. The second point, rate of disappearance of B is equal to minus rate of formation of B. Disappearance and the formation is in opposite ways, right? So what is the rate of disappearance of B? It is minus RB, okay? Minus negative positive. Formation is positive. Disappearance is negative, so you can use this one directly. Okay? Just put the negative side. So you have to pay attention to this word. What is the problem asking for? For the formation or disappearance. That is different. So following the third point at this slide, replace ratio of forward to reverse rate constant. So very often we use this replacement. This is the forward rate constant. This is the reverse rate constant. So this equation is equal to the rate constant by equilibrium constant. This one is equilibrium constant for the reaction. Equilibrium constant. Okay, so how to put a Kc into the equation? First, we can bring Kb out of the blanket. Okay, bring Kb. This one is that one, right? That one. Bring Kb out of the equation. Okay, and then this one is similar to this one, right? Sometimes the problem will only give you forward the rate constant and the equilibrium constant. So you must know this equation. Okay, the last point. We talk about a lot for reactant B, right? How about the product D? If I want to write the formation rate of D, how to do this? Formation of D are D. So you have to use a rate constant for D, okay, and following the same. Because all the reactant and the product are in the same chemical reaction. Okay, so they are decided by the same concentration, the same relation. The only different part is the rate constant. So if you want to replace the target from B to D or to H2, you only have to replace the rate constant. Okay, and also because we have this relation, right, at the very beginning of this class, maybe chapter 1, we have this relation. So that means we have this relation. So in this case, we have this relation. Okay, so that's all about the reversible reaction. Please go to the next slide. We want to verify one thing at a equilibrium. Okay. At an equilibrium, if the rate law is thermodynamically consistent. Okay, so the first one, we talk about this in two viewpoints. So first one from thermodynamics. We have one relation, Kc. Kc is the equilibrium constant, right? So AC is defined as concentration of product over concentration of reactant. You know this, right? The definition for equilibrium constant. And it is equilibrium constant, so the concentration is at equilibrium. So I write a small e here, equilibrium concentration. Okay, at equilibrium. From thermodynamics, Kc is equal to this one. Okay. Second one, from rate law. We write down a lot for the rate law, right? So considering that example, from rate law, right? The rate law, we got this, the same one. But it is a general, like a general function. It is not at any condition. So if at equilibrium, at the equilibrium, what will happen? At the equilibrium, the forward reaction rate is equal to reverse reaction rate. Okay? So we got this. Rearrange, you got a Kc. So we got a same conclusion from the first and the second point. So that means the rate law is thermodynamically consistent at equilibrium. So from the viewpoint of rate law, from the viewpoint of thermodynamics, we got a same result for Kc. So they are consistent, okay? In other words, you may say you can derive the equation at point 1. You can derive the equation of point 1 from rate law. They are consistent. The last part for part 1. The last part for part 1 is I want to talk about the reaction rate constant, Kc, Kb, K something, yeah. So next slide. The temperature dependence. If you remember the constant, like reaction constant, equilibrium constant or rate constant, they are all the function of temperature. So if you see a problem, you have to pay attention to the temperature. Okay, the temperature. So in the problem, maybe the information is at a temperature A, rate constant is like something, but the condition to find the answer, the condition is different. Maybe at a temperature B. So you have to convert rate constant from temperature A to temperature B. So pay attention to the temperature, because temperature will influence the rate constant value. Okay. So next, let's talk about the temperature dependence of equilibrium constant Kc. Arrhenius equation. So Kc at a temperature T is equal to Kc at a temperature T1 multiply exponential term. What is the order for the exponential term? Heat of reaction over constant. Okay. It is very similar to Arrhenius equation. So you can tell the difference between of Kc at a T and the T1, right? And it is related to the heat of reaction. And then I want to talk about two cases. First case is exothermic reaction. The other case is endothermic reaction. Okay, so for exothermic reaction, delta H is smaller than 0. Okay, for endothermic reaction, delta H is larger than 0. So let's verify. We have 3 minutes left. So let me verify one thing. So let's take a rest later. Okay, later. Let me explain the first thing. For the exothermic reaction, why temperature increased, the Kc decreased? Okay, so first, we have a condition that heat of reaction is smaller than 0, right? This is the first condition. The second one, if we want to talk about the temperature increases, okay, hotter is temperature increases, let T be larger than T1, okay? If the temperature from T1 to T increases means T is larger than T1. Assumption, okay? T increases, right? We want to verify Kc decreases. So the condition T increases means T is larger than T1. Or you can write the temperature increases, maybe better. Temperature increases from T1 to T. So this relation also tell you the inverse relation, right? Okay, and then if delta H is smaller than 1, also this condition, so you gotta right? You can think about this. Delta H is smaller than 0. This term is larger than 0. So multiplication, the result is smaller than 0. So we continue. We put this 1 into exponential. So exponential let me finish this part. Okay, you put a value smaller than 0 into exponential term. The order of exponential, you got a value smaller than 1. If this one is smaller than 1, Kc of t is smaller than Kc of T1. Okay. So if for the other case, if delta H is larger than 0, you will get a upside result. You can try to verify this thing using that one. Let's take a rest. I will talk about this later.喂，上课哦。So these parts are for the exothermic reaction, right? That part for exothermic reaction, when temperature increases, Kc decreases. So for the other case, endothermic reaction, I use a red color to modify, okay? They are highly similar, you know it. This one, endothermic reaction, endothermic 吸热反应. So this one become this one. This one is the same. So when temperature increases, this one is the same. But because this one become larger than 0, this one become larger than 0, right? So you put this one into this one, you got a larger. So larger. Therefore, increase. Very similar, okay? Only one condition changes. So this is for the endothermic reaction. All of the condition except for this one. This is the relation between temperature and the Kc. Okay. Next, let's talk about the rate constant. Reaction rate constant K. The name is constant, but it is not. It is not truly a constant because this can be influenced by temperature, so it is not truly a constant. So how to relate temperature and the rate constant? The Arrhenius equation. Ka as a function of t. Ka is a function of t. It is composed of a frequency factor multiply exponential term. Okay, please memorize this equation. A is the frequency factor. You have the list, right? Yeah. At the bottom, you can see A is the frequency factor. E is activating energy, gas constant, and the temperature. Okay. Also, please notice that the unit of Ka is the same as unit of A, okay? Because exponential term, there's no unit for exponential term. So the unit for them is the same. If you remember, the unit for K is different, right? In different orders of reactions. So the unit for A is also different at a different condition. So I cannot tell you what is the unit for A and the Ka. It varied a lot. Okay, so next slide. There is a figure. There is a plot. there is a plot like this. So when you see a plot, you have to see the y-axis and the x-axis first. Then you will know what it is. So the y-axis, potential energy. Potential energy versus reaction coordinate. The reaction coordinate is from, you put the reactant, you put the reactants. After reaction, you got a product. Okay, so this is the reaction coordinate in x-axis. So at the beginning, the reactant is A and BC, A and BC, okay? The reactant A and BC. During the reaction, let me write down something. A and BC, the y-axis means potential energy. So the potential energy for the reactant A and BC is energy single A plus energy BC. Okay? The energy, potential energy for reactant is like this. Okay, and then in the middle of reaction, intermediate, ABC, the potential energy for ABC is energy ABC. Okay? Finally, the product after the reaction, the product may be AB and the C. Okay, for example, AB and the C. So the potential energy for AB and the C, EAB, EC. Okay? And during the reaction, we can write a curve. We can draw a curve. So at the beginning, yeah, it is like this. Okay? The last part, we still have something, right? Between these two, what is the energy code? Between the reactant to the intermediate, the transition state, or you can call it transition state. So between them, it is EB, energy barrier. Energy barrier or activation energy. So you have to overcome this energy barrier, then your reaction can happen. Also, this one, what is this one? This one is heteroreaction. Okay, so this is what the figure can tell us the information. So you can find from the figure, you can find the energy barrier, activation energy, or you can find the heat of reaction. Okay, so last part. How to calculate activation energy. Next slide, slide 21. Activation energy is determined by experiments. Again, experiments. You have to do experiment to find the activation energy at a different temperature. Okay, so there is a figure. There is a figure in this slide. The x-axis is 1/t. Y natural log Ka. 这个有写错，是 natural log Ka 哦。The figure in your handout, it is natural log Ka. So if the equation Arrhenius, 我把它画完。There may be several curves, several lines, right, in this figure at a different temperature. So we started from Arrhenius equation. Okay, Arrhenius equation is like this. Take a natural log at both sides. Right? Natural log. You know how to do this, right? And then, if natural log Ka is y, okay, x and y, so slope and intercept. For this plot, you know the slope and the intercept. X-intercept. The intercept at the x-axis is natural log A from that equation. Okay? So every curve you have different, the x-axis is related to temperature, right? So you have many data at a different temperature, then you got this line. So can you tell which one has higher or lower activation energy? Because the slope is this one. So that means because the slope is negative value, right? Negative value. So for the absolute value, if this one is larger, means this one is larger, right? Absolute value. The absolute value means it is flat or it is steep. So for this kind of line, slope is larger, right? Absolute value. We see the absolute value. Slope is larger, slope is smaller. The more horizontal line means the slope is smaller. So for this line, low E. For this line, high E. Okay, so you can tell the relation of activation energy by using this plot. So I suggest you to memorize the Arrhenius equation. Maybe most of you have memorized this one. You memorize this one and you do the natural log. You put the natural log in the equation, you got this relation. So you know, draw this one x and this one y. You got a slope, you got a intercept, x-intercept, okay? So the smaller slope is more important for determining activation energy. If you know the value of slope, you can calculate activation energy, the real value of activation energy. So there is one example, okay? One example, want to find the activation energy. You can use Excel or other software. But when taking exam, you cannot use the software, right? So we only have to calculate by yourself. So let's see one example, determination of activation energy. 借我看一下。下一页，谢谢。再下一页。再下一页。谢谢。好。Okay, determination of activation energy. Example 321, slide 22. Calculate the activation energy for this reaction. And there is a table. The table has the relation of rate constant and the temperature, okay? And they are 5 points. 5 points. So, see this one, please plot, first plot natural log K versus 1 over T. Okay, and you can see next slide, 23. I give you the result, right? To use Excel to calculate the plot, if you have computer, you have K, you calculate natural log K. You have T, you calculate 1 over T. And you draw a line. If it is not a perfect line, you use a fitting, linear fitting, okay? You use a linear fitting, you can find it from software. So from linear fitting, we got the slope. You can see from this plot. The slope is equal to this one. And you must know the slope is equal to this one, right? Okay, so next, you can write down this at the next slide. If you got an Excel result like this, let me write down the result. Okay, let me write down the result from Excel. Okay, we got this. So first, we got is we know two things. Sorry, maybe you can, yeah. Let me write down here, sorry. Slope is equal to minus E over R. And you can take the value from the equation. X-intercept is equal to natural log A. You got the value from the equation. Okay. So first, convert the value in table, the data in table, to be natural log K and 1 over T. Draw a plot and a fitting, linear fitting. You got this one. You got the slope. You got the x-intercept. So let's calculate. Okay. Let's find the activation energy. Activation energy Let's write down the unit. Okay. Okay, write down the unit. So, this is the first answer, activation energy. Also, we can calculate A. The unit of A is the same of unit of K, right? The same unit as Ka. Therefore, the result, we can write down the relation between K and the T. So if you got this, you can calculate a K rate constant at any temperature. We still have one slide for reaction rate constant. So let's finish the last slide. The relation between rate constant at a different temperature. Okay, slide 25. So there is another useful form for Arrhenius equation. First, at the temperature T0, we have this Arrhenius equation. Okay. Second, at a temperature T, we have this Arrhenius equation. If we take the ratio, okay, this one over this one, second one over the first one, we got a This is a more useful form for the Arrhenius equation. It's the first part 1. We finished the first part, rate law. So let me recall. Part 1 is rate law, right? Rate law is to write the rate of reaction as a function of concentration. Part 1 rate law. Reaction as a function of concentration, but the final purpose is to have the relation with conversion. You believe, right? The purpose in chapter 3. Your purpose in chapter 3 is to write down the rate law as function of x. In part 1, we write down the rate law as function of concentration. So how to convert this one to this one? That is part 2. Part 2 is called stoichiometry. Okay? If you can write down the concentration as function of conversion, then you can have a rate law as a function of conversion. So that is the purpose at the second part, stoichiometry, to write down the concentration as a function of conversion. That is the purpose. Okay. Let me mention again, we have two kinds of systems. Batch reactor or flow system, right? So the flow system we want to talk about here is CSTR. For the batch reactor, concentration is equal to mole over volume. Okay, this is mole. This is volume. For flow reactor concentration, let me write down here. For the flow reactor， 你不用写跟我一样，你就自己有空间就写。我是没空间。The flow reactor concentration of A is equal to FA over V. What is the unit for FA? More time, more over time. What is the unit for V? Volume over time. Okay? So the same, we want to get a concentration, but in different reactors, we use different parameter to calculate it. But they are similar, right? Also, mole over volume. But flow reactor means there is a rate. Rate is related to time. So it is the molar flow rate over volumetric flow rate. But they are the same. So if you see a batch reactor, you have to write Na. You see the flow reactor, you have to write the Fa. Okay, so next, let's consider a general reaction. AABB becomes CC and DD. From stoichiometry, we have a relation, right? The relation between RA, RB, RC, and RD is very simple. Because the name for part 2, the topic for part 2 is stoichiometry. So the relation between the reaction rate is their coefficient. Okay? The relation between the reaction rate, the coefficient. And commonly we will take the coefficient of A to be 1. Usually if A is the limiting reactant, usually we will divide the coefficient of A. This reaction is better. This form of chemical reaction is better because the limiting reactant A, the coefficient is 1. Suggest to do this. Okay, so let's go to the batch system. First, let's talk about batch system. Batch system first and CSTR. So now it is not a flow system, batch system. There is a scheme, right? There is a scheme. Next slide, next. There is a scheme at slide 下一页. 好. Slide 28. Okay, so there is a batch reactor. I hope you remember. For batch reactor, we talk about time, right? For batch reactor, we talk about time. For flow system, we talk about volume. So for batch reactor, at the beginning, we have ABCD, right? The reactant AB, products CD. So at T equal to 0, we have Na0, NB0, NC0, ND0. And also one extra term is called Ni0. This I inert. It is like nitrogen or argon. It would not react. Okay? So A, B, C, D can react with each other. But one different kind of material, I, is like a environment, to produce some environment. So the inert will not react with A, B, C, D, but maybe some inert will put in the reaction. Okay, so after reaction, if T is equal to T, we got a Na, Nb, Nc, Nd, and Ni. Okay? How will we do at the next step? We want to create a stoichiometric table. And next slide, 29. But I want to say something at 30 and 31. 我们先去30、31，我应该把30、31放在29，但我每一年都忘记30，这是30，对。Let's finish slide 30 and 31, then go back to 29. Okay. So the purpose is to write down the stoichiometric table. This one will be written at slide 29. But let's first start from 30. 30, calculate the number of moles of species B at a time t. Okay. This one should be done here. But now, let's go to page 30. Okay. So first, assume this is the mole number. Okay. Assume this value of A are consumed. Is the first condition, okay? And second one, you know, from the reaction, the coefficient is 1 and B over A. So 1 B over A for each A reacted. We have, for one more, it is better. For one more A reacted, we have B over A more B reacted, right? The relation between A, B. So, you can write down this one. Moles B reacted is equal to moles B reacted over moles A reacted multiply moles A reacted. If you put it as a symbol, B over A, NA0, X, we have this relation. Okay, the third point. Third point at slide 30. The number of moles of B remaining in the system, NB. Remaining in the system, what is NB? NB, remaining means beginning. At the beginning, NB0 minus the reacted number, right? So you got this relation. It is a conclusion. So we have the information of A, but we have to calculate the moles for BCD. So you must have to know the relation between B and A, or C and A, or D and A. So for B, this is the final moles. Is equal to initial moles minus the reacted moles. The the reacted moles should be related to Na0 because we can decide Na0. We decide what is the amount of limiting reactant we put. Limiting reactant. So Na0, we can control this one. So we want to write down the equation related to Na0 for Nb, Nc, and Nd. Okay, so similarly, you can do this for Nc, Nd. Okay, Nc, Nd. Okay, so go to next slide, 31. Slide 31. So after talking about the moles for individual species, let's talk about the moles for total moles, okay? Total moles. So stoichiometric coefficient, let me write down first. Slide 31. NT means total moles. It is equal to NT0, the initial moles, initial total moles. NT0 multiply something. Do you understand this one? The total moles means you sum up Na, Nb, Nc, Nd, right? Actually, this one is Na, Nb, Nc, Nd. Ni, okay? The final moles. This one is Na0, Nb0, Nc0, Nd0, and Ni0, right? This is the changes, the reacted moles. I will not react it, right? I will not react it. So you cannot see any information for I here. You cannot see. But you can see this one is for A. The reacted moles for A. The coefficient is 1. For B, for C, for D. And you sum up these 4. That is the reacted, total reacted moles during the reaction. And then given the symbol, we use delta to replace the coefficient. So next, given the symbol, okay, we use delta to replace coefficient summary. Okay, so finally, the total number of moles can be simplified as okay, so let's write down the stoichiometric table next week.